We start off what we know. They gave us the mass of the hollow cylinder, the radius of the hollow cylinder, mass of the solid cylinder, that's S, times the radius, not times, but also the radius of the solid cylinder. And we're also going to put another variable, h naught, because that's the height in which they're going to start from. This may or may not be useful, but at least I'm going to list it here just in case. And v naught, which is their translational velocity as they start out, is going to be 0. So what we're trying to find is if the final velocity of the solid cylinder is greater than, less than, or equal to the final velocity of the hollow cylinder. We're also going to look, basically, I'm just going to get rid of the finals and we're just going to say Vs greater, equal, or less than Vh. Since this has to do with masses and velocities and whatnot, I'm going to go ahead and use the conservation of energy equation. Um, we know that the cylinders will start off at a certain height, go down to the bottom, and in that process, gain both rotational and translational kinetic energy. So I'm going to skip a few formal steps and just say that UG in general is KE translational plus KE rotational for each of the two spheres. And then I'm just going to break it up into two sections. I'm going to go ahead and have my hollow sphere here and my solid sphere here. I'm going to analyze their conservation equations, try to find out their final velocities, then compare the two. So that's the strategy that I'm going to conduct right now. So here is the conservation equation for the hollow cylinder. Oops. So rotational. Okay. And then for the solid cylinder, if I have any room left, those will be right here. Okay. Okay, so now for this, just like in the previous problem I did, my main point is to try to get rid of as many variables as possible. So let's get I and omega in terms of M's and V's. And we can invoke kind of the same strategy we did last time. If you didn't look at my last video, let's do it again. So I for hollow cylinders ends up being mr squared. Whereas I for solid cylinders is a little different. It's 1/2 mr squared. So now let's go ahead and write that in. It's going to take up a lot of space. Then we'll cross out a few things and hopefully reduce this equation into a more doable length. So we got mh h naught equals to 1/2 mh vh squared plus 1/2. And now instead of I, I'm going to write mr. Okay, now for the solid cylinder, let's put a little line here. It's going to be mgh is 1/2 mv squared plus 1/2. I'm going to go ahead and just consolidate this right off the bat. It's going to be 1/2 times 1/2 mr squared. So I'll just say 1/4, just so we can save a little space. Mr squared and then omega squared. Great. So this is the longest we'll get it. Let's go ahead and start canceling a few things out. Actually, let's go ahead and do one more step. Again, we're going to see how the cylinder or both cylinders as they roll going to basically look like this. You got the r vector, you got the velocity vector, and then you got the omega vector as it's rolling. And it looks like since it's rolling this way, the omega vector is going this right here down. So if you take the fact that V is omega cross R, you'll see that V will go to the right. Omega is going down. Um, so omega is going down. R is going up, and my apologies, I made a small mistake. Actually, at this point of the wheel is actually going to go this way at a velocity v, and that's kind of the trick there. Because this point of the wheel is going at a velocity v this way as it's turning, the wheel itself is going to go this way. So that's basically why when it turns this way, the wheel goes to the right, though this aspect of the wheel with respect to the center is going to go to the left. So given that mechanics, using the right hand rule, this plays out. And also, they're all perpendicular. You got R going down, you have V going to the left, and you have omega going into the page. So you can simply say that V is equal to omega R. Now, using that, then you could say that omega squared R squared, or omega R quantity squared, will just equal to V squared. So what we're going to do is we're going to go ahead and cross this off and call that VH squared. We'll do the same logic for a solid cylinder, cross off R omega squared, and say that's Vs squared. Next thing we're going to do is we're going to take out all of these M's, because you're going to cancel them out because they're consistent across all terms in the equation. And that's basically all we have in our bucket of things to do. Now let's go ahead and rewrite the equation in a more simple form. GH is 1/2 VH squared plus 1/2 VH squared. That's for the hollow cylinder. And then you have GH is equal to 1/2 VS squared plus 1/4 VS squared. If you have enough foresight, you could probably see where this is going. This ends up being VH squared. This ends up being 3/4 VS squared. And so now going ahead and isolating the V's, we're going to get that VH is the square root of GH. But VS is going to be the square root of 4/3 GH. Which one's bigger? Well, since there's a 4/3 in front, that's greater than the 1 that's in front of this GH, then this VS is greater. So the final answer is that the translational velocity of the solid cylinder is going to be greater than the translational velocity of the hollow cylinder. And that's going to be at the bottom of this ramp.